Hi, so this is lecture 5. We're going to start talking about metabolism. This is a big topic. It's a really important topic in physiology overall. And so we're going to break this up into a couple of lectures. The main one we're going to be talking about today is this glycolysis process that we can see on this slide here. Again, the lecture prepared by Dr. Pipal. Alright, so to understand why we're talking about metabolism, metabolism is really about understanding chemical reactions, but understanding chemical reactions requires understanding a lot about their energy, the energetics of what's happening and why. Energy can be defined here as the capacity to do work. So when we're talking about metabolic energy, we're talking about the body's or the cell's ability to do work. Now, what kind of work does a cell have to do? Well, it turns out there's a lot of different kinds of work. One is chemical work. Chemical work is the process of making and breaking chemical bonds, where a lot of times, especially when we need energy, we're building something. So we're making new chemical bonds and putting things together. So here, two different reactants being put together to create a product. That is a building or synthesis kind of a reaction that usually requires some kind of energy. Transport work involves moving things across and through biological membranes. It's especially important to use energy if you're trying to create a gradient. And we're going to be talking about that coming up when we start talking about membrane physiology quite a bit. Also, mechanical work, that's just like movement, right? So, for example, moving muscles, using muscles to move things around. Inside cells, there are similar processes that literally allow for movement of things around inside the cell. Those are some examples of the kind of work that needs to be done in a cell. And a lot of times it takes energy to do that. So in the same way that your car needs electricity or gasoline or diesel or something along those lines to be able to go, you need to put that energy source in there. And then the car can extract the energy through its motors and engines and use it for all the things that the car needs to do. Cells need to be able to do the same thing. They have all this work they need to do, and they're going to need energy to do that. Here's an example. So there's chemical work. Here's an example of transport work of things being moved across a membrane. You might remember from our very first lecture, we talked about how things flow down a gradient. And so here you can see this one looks like there's a lot more of these squares, this solute on the outside than there is on the inside. So they're going to want to flow from out to in down their gradient. The membrane prevents that. And in this case, it looks like the cell wants to get more of it out, which is the wrong way. So it's not going to want to go that way. So in order to get it out, you have to pump it out using energy. So the same way, like if you want to, take water out of the ground, you're fighting gravity, you have to put energy in, either mechanical energy of a hand pump or using electrical energy to get that water to come up out of the ground. Same thing happens here. If you want this to go, against the concentration gradient, you need energy to do that. Mechanical work, we're going to be learning a lot about the actin-myosin connection here and how energy is used for that. But you'll notice in each of these cases, ATP is being shown. Right? ATP is the energy source that's used for most cellular things. Before we get into where the ATP comes from and how it works, we'll talk a little bit more about energy in general. You hopefully remember this from your chemistry class, this process of understanding a energy diagram for a chemical reaction. So this is showing an example of one kind of reaction called an exergonic reaction. The reactants have a certain amount of energy. So this is the energy that they have. Usually most of that energy will be stored in the chemical bonds. It's kind of a kind of potential energy. And then here the products have a lower level of energy. so they have less energy in them. The difference between the reactant energy and the product energy, this difference here, is referred to as the Gibbs free energy. Free not as in it doesn't cost anything, but free as in available. So when this reaction happens, there will be this much energy from the reactants to the products. There will be that much energy that gets released and can be used for something else. So that's the Gibbs free energy, often abbreviated with a delta G, is the amount of energy that could be used to do work. Okay, so exergonic reactions like this one shown in the top picture are generating a net release of energy. So there's a release of energy out there that can be used for something else. Some reactions, however, are endergonic. An endergonic reaction shown here, the reactants have a certain level and the products have more energy. So in order for this reaction to happen, they are going to need an input of energy. They need energy to go into the reaction. A couple of examples of these kinds of things that you might be familiar with. One that I like to use is like if you burn something. Burning something, what will happen is the paper or wood or wax or whatever you're burning, like in a candle, is going to have a certain amount of energy, and as you burn it, that's a chemical reaction. It's combining with oxygen, producing carbon dioxide and water, and as you burn it, there's going to be a release of energy. That's the heat that you're feeling as you burn it. That's the energy. Now you could harness that energy, right? You could just like burn it, and then all the energy just goes into the air. But you could actually harness that, right? That's how stoves work, especially gas stoves or wood stoves, right? The amount of heat there, now you can cook your food, you can boil water, you could drive a steam engine that way, right? So there's a lot of work that could be done by harnessing the heat of that as it burns off. Another example, this is not technically a chemical reaction. I've had a hard time thinking of a chemical reaction that would really that most of you would be really aware of and have experience with. But state changes work very similarly in terms of the energetics. And so what I mean by that is water turning into steam. So the process of boiling water and turning it into steam, that's not technically a chemical reaction because it's still water afterwards. The water didn't change, but it changed from liquid water into vapor. And that state change also works very similarly to these energetics. And so using that as my example, if you need to boil water, water has a lower energy level than steam does. So if we think of water as a reactant and steam as the product, again, it's not truly a chemical reaction, so it's not actually reactants and products because they're not chemically changing. But hopefully you just kind of follow along as the same idea. If you are boiling water, you have to put energy in for that to happen. Somehow you're going to have to put energy in. And so to get that to happen, a lot of energy has to be put in. The thing that happens when you have an endergonic reaction that needs a net input of energy, if you stop putting energy into that, the reaction will stop. The same way that if you're boiling water on a stove and then you turn the stove off or you take the pot off of the stove, the boiling stops. Right? As soon as the heat has gone down enough, the boiling will stop. Whereas an exergonic reaction usually doesn't stop. So like if you had a piece of paper and you light the piece of paper, you don't have to keep lighting it. You don't have to keep putting a lighter there or a match there. Once you've got it lit, it's just going to go. And it's going to consume all of that. So that's what happens for exergonic reactions is once they get started, they generate enough of their own energy to keep going. Whereas in endergonic reactions, you have to continually be putting energy in. One thing that happens in the cell is it's possible, and this is usually how it's done, exergonic reactions can be used to drive endergonic reactions, meaning that as the energy is being released from this exergonic reaction, that energy could be used to supply this difference to allow the endergonic reactions to occur. And so we do have a lot of endergonic reactions that need to happen in our cells. And the only way to get them to reliably happen is to provide energy for them by coupling them with exergonic reactions. One last point, kind of the top point on here, I did these a little bit out of order because it just made more sense to me right now, is the concept of activation energy. So you notice I started talking by just saying reactants are at this high level, products are at this low level, so there's a difference. It's exergonic, there's going to be this energy release, but I totally ignored this big hill in the middle for the first 5 minutes of me talking about this. This is called the activation energy. What happens is, in order for this reaction to even start, you need to put in a little bit of energy to even just get over this hump. So if they don't have enough energy, then the reaction's not going to happen. That's why we have something that's really burnable, like paper. Burning paper is the reaction of paper with oxygen from the air. That's the reaction. Paper plus oxygen. Well, I have this piece of paper. If I have a piece of paper, there's oxygen in the air right now. It's not burning. Why not? Why isn't this burning as I talk to you right now? Because even though the reactants are all here, even though this is an exergonic reaction, it still needs enough energy to get over that activation energy. And there's not enough energy right here for that to happen. So the way we can provide that is to give it a little spark or to light a match. And that is providing the energy to get the reaction started. Once it starts, that piece of paper is going to burn right up. But that's called activation energy. It's the initial energy needed for a chemical reaction to occur. And it's basically the reason why most chemical reactions aren't just happening all the time, because there is a barrier, even if they're exergonic. All right, so this is basically showing the combination of an exergonic reaction releasing energy and an endergonic reaction requiring energy. A big exergonic reaction is going to release energy, and so you can see there's maybe a little bit of excess energy left over even from this, so that means the endergonic reaction shown in blue had enough energy to go forward because the exergonic covered it. All right, one way to deal with the problem of activation energy, it is a problem because life needs these reactions to happen. There's a lot of reactions that have to happen in a cell, and they have to happen pretty fast for cells to stay alive. You can't wait for them to spontaneously occur because activation energy is going to prevent most of them from ever happening. One example we're going to talk about today is how cells use sugar, glucose, to create ATP, which is an energy form for the cell, right? And so the cell needs to be able to do that. It needs to be able to take that sugar and convert it into energy quickly. But if you have sugar in your cabinet at home, in your kitchen, it's still going to sit there and just be sugar, right? It's not changing. It's not turning into energy in a different form right now. And that's, again, because of the activation energy. So one way that cells deal with that, the primary way cells deal with that, is to use enzymes. What enzymes do is they actually lower the activation energy. They don't eliminate it. They don't provide energy to the reactants. This is not making this more exergonic or anything like that. The actual exergonic reaction stays exergonic in the exact same amount. But what the enzyme does is, instead of it having this really big activation energy barrier shown in red that it has to get over, it has a much lower one shown in, I think this is blue in here, with the enzyme. And so it just means that it needs a lot less energy to get started, which means it can happen a lot faster. The main reason this works is the enzyme will actually position the substrates. Again, substrate is the molecule that's going to be reacted on. It's going to position the substrates to increase the likelihood of the reaction occurring. It kind of helps bend them a little bit to sometimes to kind of bring them closer to that like intermediate state where they're going to go into becoming products. Increasing the enzyme concentration will speed up the rate of a reaction as long as there is enough free substrate available. So obviously more enzyme means there's more active sites, meaning there's more reaction can happen. Increasing the substrate concentration will speed up the rate of the reaction if there's free enzyme available. So basically it's just saying if there's enzymes floating around that aren't doing everything every second, but you make more substrates, now they'll be available to do more, and so they'll do more, right? That will cause the rate of the reaction to go up. Sorry, these are the pictures for that. So we have two different things going on in this graph here. One is the substrate concentration is on the x-axis, rate of reaction on the y-axis. So as substrate concentration increases, the rate of the reaction also increases, and you can see that. The blue line is showing what happens when you have more enzyme, the red line when you have less enzyme. So you can see that the rate of the reaction goes up more slowly when you have a lower enzyme concentration, and the rate of the reaction goes up more quickly when you have a higher enzyme concentration. If you think about all of those parameters, it makes sense, right? The more active sites that can do the reaction there are, the faster the reaction is going to go. That's really what that's saying. And then also the more substrate there is, the more the reaction is going to be able to go. However, there will be a point where the substrate concentration will no longer increase the rate of the reaction because the free enzyme is gone, is used up. So it's not used up, it's there, but it's just the enzyme is going as fast as it can. There's a point at which the enzyme just can't increase the reaction rate anymore because it's just, there's like as soon as the products leave, a new substrate's in there and it can't go any faster than that. And so that's what we call saturation. So saturation, you can see, again, this is the same graph basically as the one above. Substrate concentration on the x, rate of reaction on the y. There is an increase in the reaction rate as the substrate goes up, but then it slowly starts to taper off until it reaches a point where it's not getting any faster even as you increase the substrate. We saw the same thing in this graph too, I just didn't really mention it. It's kind of approaching this line. And that's the maximum velocity. Obviously the maximum you can see depends on how much enzyme there is, but for a given amount of enzyme there's a maximum because it gets to a point where it just can't go any faster. It's like as soon as the product leaves, there's already another substrate right in there, and that's called saturation. I'm going to pause here.